Okay, so yesterday we had some time out. So I think what we did here, there's something that take a long time. I think this is because of this. The check here has to go into this. So I wonder if we should look at the psycho detection stuff. We have a directed graph, right? Yeah. Master space algorithm. Hmm. Hmm. So we do depth first search, this is what we do. But right now, our we doing iterative version. We don't have the stack to unwind for us, eh? We're gonna create one. Let's call this stack rank. We're gonna implement like they do here. So we have visited and finished. Right. So let's call this visited finished. Right. So this is actually a map, right? So that we can be faster. So let's call this or can we just use it as the set for now? Right. So right. So we want stack dot and we do I right. Started with I, right? So why stack is not empty is we want to track. Of course, we're gonna have visited dot add here we say finish, or if visited, then with that, okay. If node in finish, then we continue, right? Okay. How do you know when we finished? Right, so we know when we finished is when we came across this again after we visit all the neighbors. Right, so somewhere here we gotta finish. Right. And the visited.add, right? So cycle is detected if node is not finished and node is in visited, right? Then we break. Right? And finished. Right, so we go to every neighbor for right, let's call this neighbors for graph of node, right? For I in graph, right? Right, so we start with this, we pop one, and if it is finished, no, then how do we know? Oh, that means we should track the node, right? Because like 0, 1, right? So let's look at some of the example we have here. So first we got 0. We push 1 and 2 on the stack, right? If not neighbors, then this is the terminal node. We can do is terminal node dot add per node, and we continue, right? And also finish add, yeah. Else we loop to the neighbors, we add them to the stack, right? So 0 gonna get 1, 2, right? So 1, 0 is crossed off. 1 gonna go to 2, cross off here. Okay, so if it is in finish, then we know it's done, right? So that means we probably have to add them back, right? So in this case, we got 0, 1, 2, and 1 is processing. We want a 0 here, right? Because after we process 1 and 2, right? So 0, we also have to append back, right? Because we want to visit all the node, right? So when we visit all the node here, we know that we have to come back here, right? So like we need a way to say that, okay, we need a way to say that, okay, after we finish process this, right? We visit, but we have not done processing yet, right? So with this, after we finish all the children, we want to come back here and say that we finished, right? So we want so let's track them, right? Visited 0 and finished. Right now it's nothing, right? So we have first we have 0. I'm gonna add 0 to visited, and 0 expand to 1 and 2. And we pick up 1, put 1 in visited, and it will add 1, 2, 3, right? Yeah, and we pick up 2. Oh, okay, hold on, this is wrong here. So we want to do depth first search, not breadth first search, right? So hold on. Okay, we start at 0 again. Put 0 in visited, and we want to push in the reverse order, right? We want to pick up 0, right? And 1, 2, we want to add to the front, right? So 0 got 1, 2. So this will be 2, 1. Right, so neighbors first, right? So it will be 2, 1. So we pick up 2, 2 is visited, gone, right? So 2 can go to 5, right? So 5 here isn't visited. And 5 can go nowhere. So because 5 can go nowhere, 5 can go nowhere here, right? Five can go nowhere. That's done. Done one note, right? So now we pick up 1. So we do the same thing, but eventually we want to go pick up 0 again, right? Because now we can say if note isn't finished, how do we know it's finished? That's the thing, right? So I think we want to stack a pen. Because if we add finish here, we never see 0 finish, right? Right. Right. So we go 2. We go to 5. Cycle found, right? This terminal node, right? Okay, so 1 can go to 2 and 3. Wait, hold on. 0, 0, make it become 1. So we want to be able to say after 1, 2 finished, we know that 0 had to be picked up again. So which is why we add. How do we know when it's finished? See, finished is after visiting all the neighbor of itself, right? So that means we look to all neighbors, we do FDFS on them. Only when after we done with them, which is why we need to add a 0 here, right? So I think we can when do we add finish? Or do we track the parent? So the idea here is 0, gonna do that. So 1 gonna expand to, we add 1 here. So 1 gonna go to so 1 gonna have 2 and 3, right? 2 and 3, right? Because here, right? So then we want to be able to pick this up again to mark them as finished, right? 2 here, we go to 5, and then we put a 2 here, right? So now 2 here, also go to 5, and mark a 2 here, right? 5 can go nowhere, right? So then that is go to the next. So we have this gone, 5 is gone. After 5 we go back to 2 here, right? So when we go back to 2, how do we know it's done? Okay, let's just simplify things a little bit. So when we go 1, we know there's 2 and 3 that we can go, and we need to pick up this because after we visiting all this, we come back to this. So when we come back to this, we know that it's done, right? Oh, so then when we do this, we know finish can add a node, right? Right, so that. So pick up 2, we do the same thing, add 2 at the end, put a 5 here, and we pick up 5, we added a 5 first, and pick a 5 down, then 5 become finished, right? So now a 2, we pop 2, so right here we have to pick, right? So seems confusing, guys. Okay, let's do one thing. Let's start at 2. We take 2 out and we added 5 in front, right? We have to add them back in the stack, right? Stack dot pen, right? So now we pick up 5, we put 5 on top of the stack, and we put 5 back, right? So we pick up 5, we cannot visit anything, we mark 5 as finished, and we see infinite 4 done. So now we back to 2, right? So right now 2 is in finished. No, how to know when finished? We can go to 5. So we want to go through all this. After we go all this, we want to know how do we know, right? So 2 can expand to 5, right? 5 is done. I mean, there's no neighbor. Its terminal node is finished. Gone. So now how do we know? Which is to say that when we loop to this, if any of the neighbors is done, it's already finished, right? So if we finish, we only finish if all the neighbor we visit, yeah, right? So 5 is done. We need to have a way of marking, right? So let's add. Maybe we don't need the second set, right? So according to this cycle detection thing, we want to do the iterative version of this, right? Right. Or for the sake of this, we just implement like this. Let's do DFS with the without the with the recursive, no? Yeah, let's do that. And then we can look at the iterative version later on. We have some version here, but seem like it take too long because I think the problem is when we check this, we iterate to all the things, right? So we're gonna do DFS. What do we do here with the V? And we basically, let's see, okay. Right. So we can convert this to Python. So basically, if V in visited in finish, return, right? If V is in visited, then we found the cycle, right? The Y we mark them as visited. And then we copy this. Right. So then we do finish, add V. Right, this should work. So then instead of this, we do okay. So now we do DFS on the I. Right. So this should work. Yeah. So okay, so start at these. We do DFS. If we found the cycle, then okay. So this would do DFS of neighbors, right? So we started these, we do all these. If it is finished, then what is this? Okay, right. So we keep doing this. When do we mark them as finished? Okay, so this is actually, we don't need this. Okay, I for I in range of len. Oh, let's just do this. Result equal this. Return. Right. So if I in visit infinite, right? Then result dot add I, right? Yeah. Let's try this. Oh. Oh, grab V. Oh, we have so many test cases. Oh, pen. Okay, something wrong here. At least this one doesn't time out. But let's see. Okay, so Y. Okay, let's print visit V current finish visited. Right, let's see. Zero, good. And one. So 0, 1. Visit 2. Okay, 0, 1, 2. Oh wait. So 0, 1. Okay, 1, 2. Good. And 5. So 0, 1, 2, 5. So then we back up 0, 1, 2, 5, 0, 1, 3, right? Yeah, we got 3 here. 3 go back to 0 here. Then finish. Finish is 2, 5. Go back to 3. We visit 3. And then we visit 0 here. Right? So Horizon has the cycle here. Okay. Cycle cycle. We did. So when we do, we see the cycle. Okay, I see. We actually should return false, right? So if this detect the cycle, then we break. Otherwise, we continue. So here we gotta say all visited, right? False, right? So this is true. Right? Do we want? We still traverse all the graph, it seems like. So our finish is 2 and 3, 2, 5. If I in finished, so 0 is not in finish, right? So we still visit 2, okay. Hold on. Let's do some printing here first. Do this. Okay, after the DFS, we want to print the I, and we want to print the finish. Visited, right? Right. We detect the cycle, whatever, then if we detect the cycle, we want to end here for 0, right? Right? So with the way that we doing here, we gotta say if not, right? Found the cycle, then we return false here, right? To stop the, okay. So this, we didn't do 2. Is it 2? So this is finished, and do we have to redo this for every vertex? Good. Cycle. Do we have to undo the step that we're doing here? So as soon as we expand 0, we go to 1, go to 2, we go to 5. So when we visit 5, so let's just call the after here. Finish after So we finished 5. Oh, so that means this is good. There we go. So after we finish, we got 2 5, and we visit 3. When we visit 3, it point back to 1, point back to 0, and 0 is in visited, right? Right. If not, okay. So then the outcome is 0 got this. Yeah, 0 can only finish 2 and 5. And when visit 1, right, we only finish 2 and 5. If it's didn't finish, then it's okay. So 1 can go 2 and 3. 2 finish, okay. Visit 1. Okay. Okay. Nice. That should do it. I think you might not need these. Right. We can literally do this. If not this, right? We do this, right? If DFS, right? We just need this, right? Go. Submit. Let's see. Yeah. Oh my god. So can we implement this is a recursive, right? So let's do def. This is the recursive, right? So we will do all of this. Right. Turns out dot recursive graph. Right. So we want to do a version for iterative, right? Let's call this iter. And so the challenge here is we don't have the stack to do we still have those. But we want to maintain them in the stack, right? Because that's the nature of function call, right? But let me take some break. me get some water. Okay, so we want to simulate the situation like that. So essentially we want to have this is recursive solution, iterative solution. I think the iterative would be good. Okay, so this is the main logic that we have. So we want to do stack. I'm gonna start with I, right? With the, let's just call this V so that we in comply. Why the stack is not empty? I'm gonna copy this. Okay. So out here we can do it if the stack is still not empty. I mean we can append this. Okay. So V equals stack dot, what is it here? So pop, right? And we go to all the neighbors. To I here. Yeah, we can do V in here. Oh, we don't need this. Right, so we want to also visit them first, right? So that means stack.append neighbors, right? So we want to visit in the same order. Oh, we pop front, right? And how do we know when it's finished? The problem here is we don't have the recursive one here, right? So okay. So that means we have to somehow came across that again, right? So that means after we do that, we stack append house B as well, right? Right? Okay, so first we check if v isn't finished, then we don't have to expand them. If v isn't visited, then we break. Otherwise we do add them to visited, right? And then we expand them. We also add this. So when we came across again, we know that we can continue. But if we see them in visited, then so if it is not in finished but it's already visited, then that is, let's do this and see what going on here, guys. Oh, not stack. Sorry. Something is wrong here. Let's do this. Some debug. Print cycle. This is what? Cycle here. Print. On my landlord, send me something. Do what is it? 3 p.m. maybe? Wait. We cook to 2, maybe 3 p.m. 3:30 p.m. Okay. Let's check out. Going on here. So visit 0, 1, 2. Oh, we visit 0 again. So visit 1, good. Let's just print stack here. Let's see. So 1, 2, good. We need to add in the front, I think. Right? So we want neighbors for stack, right? And we add 0. Right? Okay. So we got 2 1, good. 5. We should also print the current state of the finish and the visited. Okay, 0 2, good. 0 2 5. Finish. And wait, so we can only edit finish if it is in the you finished all the node, right? So does that mean two 5 1, right? 0 2 5, and then we do 1 3 and 0 again, which is in the cycle, right? So this adding here is wrong, right? So if somewhere along the line here, if it's a cycle, then we don't want to add finish here, right? So we go through all the neighbors and visit the neighbors and so on, so on. We only add them to the finish if we can visit all the neighbors, right? That's probably mean that we should we track the parents or no? Right? So we trying to match with our recursive, which is easy, but the iterative requires to do some tracking, right? So we want to visit all the node in this order, so which is what we have. So 0 2 1, whatever this is, and we only can get finish here if we visited all the node in its stuff, right? So we add them okay, so we shouldn't add them here. We want to keep track of that, and we say in finish or if this children is in finish, right? So then or length of graph v what am I trying to program? I'm just doing lead code, my friend. Just doing lead code, my friend. So we add this, do this, and we want to add them in the same order. So let's just do reverse. Right. Right, so now our version still not tracking finish correctly. Right. So we want to know, when do we finish? Right. So one thing we can do is so when do we mark something as finished? We finished if all the oh no, this is Python. This is not C. Good luck with C then. So we want to know, when do we finish in the version that we have here, because we keep going down the stack. It will mark the finish here if none of this is false, right? So that means when we set V here and then we check if it finished by looking at the children if they are finished, right? That's what I'm thinking. Or oh, thank you, have a good day. Let me follow you too. Subscribe. Thank you. Have a good day, my friend. How do we do a def assert version of this stuff? Right? Pop. Which is what we did here, right? We pop. We add them as visited. From V to W, push, yeah. So the problem is, right now, let's just do the check then. So if we progress this way, we get to 5. We will do this. And okay. So if not graph, then basically we can finish .add right away. So that's give us 5. So we go back to 2. Right here we have to check out children here. Then right, or length of this thing equal length of the children, right? Of the neighbors. So n for n in neighbors, n for n in neighbors in in graph. V is V and in visited, right? Right. If we go to 0, go 1, 2, good. And 1, go 2, good. none of them finished. So we got 2, we got 5. 5 finished, good. 3, 5. What? 3 can go to what? So visit 0, 1, 2, right? 1 go to 2, 3. 1 go to 2, 3, good. And then 2 go to 5, right? 5 finish, yeah. Okay, add it to the 5. Then go back to 3. 3 can go to where? 3 go back to 0. Right? Okay. 3, 0, 1, 2, 3. 3 go back to 0. Finish. Why is it finished? Or length of so visited is 0, 1, 2 already. BC3. Why is it finished? Oh, if n in finish, this is the one. Okay, so we still got 1 for some reason. So out here, what happened here? Print of I and stack finish visited. Oh, we can move this. So what? Okay. So print. So we did not finish 3, right? That's wrong. So 0, 1, 2. Pick 1. We pick 1, then we finish 2. 0, 1, 2. So 0, 1, 2, 5 is good, right? But 0, 1, 3 is bad. So 3 shouldn't be in finish, right? But it's in visited. Oh, visited. This is visited. So we found the cycle, right? Then 0 is not added. Okay, start at 1. Cycle. 1 is in finish, right? 1 is in visited. Yeah. Oh, not stack. And I is in finish, right? We got 1 somehow. So case 3. Right, so maybe we can fix this. That should be good. So what does the graph look like? This is 0. Go back to 0. Okay. This is cycle here. So we did detect them. We missed a 1. So 1 go to 0. So go to 2. Go to 3. Go to 4. 2 go to 3. We go to 4. And 4 is the final state. Oh, 0 is the final state. Okay. So what happened with 1 here? 0 is finished. Good. Cycle. Where? One can go to 0. Good. Finished. So this is finished. Visited. 0, 3, 4, right? Yeah. So the order here is we got 1, 0, 2, 3, 4. Good. Finished. Good. And then 3, go to 4. Good. Right? And then 0, 2, 3, 4, right? 0, 2, 3, 4, good. 2, 3, 4, good. And then 3, 4, right? And then we back to 1. 1's already visited, sure. So 0 go to 0, 2. Is 2 not in finish? Okay. 0 here. 2, 3, 4. 2, 3, 4. Yeah. 2. Yeah. Got a 1 here. And we pick up 2. Oh, we have to add 2 here. Forgot. So basically, so neighbors gonna be first graph of V plus different V, right? So there's gonna be neighbors that. Maybe this will work. Right? Okay, fine. Now it's wrong. 5, 6. What? So we got what? 1 here. So okay, 1 go to 0, 2, 3, 4. Oh, you gotta add 1 at the end. Oh, this one. Right. There we go. Let's see if this version actually better than the other one. Right. Okay, we still print stuff. Okay. So let's submit this and see if we can beat the old one. Yep. Okay, we beat it. Iterative solution actually was. What? We done something wrong then. Submit again, maybe? Whatever. See. See, we did so good here. So maybe keep recursive solution. Because maybe Python optimize fine. Right? Alright. So let's go look at some programming subreddit. New today. Do not some kind of supply chain attack, it seems like. What is this? Oh, hello. Sorry I didn't see you. Shal TM. I think I'm just gonna stop here now. I have to cook some stuff. We'll try to be back later and do the Substack post with maybe solving this median up to sorted array. Then it'll be good. Right, that's it for now.